Hi there. So in this video, we're going to be looking at a strong acid, weak base titration once the equivalence point has been reached. The question in particular asks if 30 milliliters of a 0.2 mole per liter solution of ammonia, which is a weak base, is titrated with 0.4 mole per liter hydroiodic acid, HI, determine the pH of the solution at the equivalence point. We're also given the Kb value of ammonia, which is 1.76 times 10 to the negative 5. So note that ammonia is a weak base and hydroiodic acid is a strong acid. Okay, so to get started, we always write our reaction equation. So let's do that first. Okay, so you can see I now have my reaction showing my products that are formed from my initial reactants. I know that my products will be ammonium ion and iodide ion because of the fact that I'm working with an acid and a base. My acid will donate a proton to the base, which results in the formation of the ammonium ion and leaves behind the iodide ion. So, now that we know the reaction, we can compare the molar amounts of each of our products and determine how many moles, the molar amounts of each of our reactants and determine the molar amounts of products formed. Okay, now in the question we aren't given the molar amounts, but we are given the concentration and volume of ammonia. So let's solve for its moles. So you can see that by multiplying the concentration by the volume, I will solve for moles because liters cancel. Keep in mind that I needed to convert 30 milliliters to liters by dividing by 1,000 before completing this calculation. Now that I know how many moles of ammonia I have, I can fill that in my initial row of my ICF table. Now to determine the moles of hydroiodic acid, if we look in the question, we can see we're only given the concentration. We aren't given the volume added. However, because we're told that this situation is occurring at the equivalence point, we know that we need to react all of the acid and all of the base. At equivalence, we have to neutralize all of the reactants. Therefore, when ammonia reacts with hydroiodic acid in a 1-to-1 molar ratio, we'll need 0.006 moles of hydroiodic acid to neutralize the base. Given that we have equal molar amounts of our reactants, I know that my change column will have to use all of the moles of both of my reactants. Which therefore leaves me with 0 moles of either. However, we do have to keep in mind that those moles will form product. In this case, we'll get 0.006 moles of ammonium And we would also form iodide ion. However, because the iodide ion is the conjugate base of my acid, and my acid is a strong acid, it's going to have a negligible impact on the pH, so we can ignore it. Therefore, in my final molar amounts, I will only have 0.06 moles of ammonium ion. Because I know how much ammonium ion I've formed, I can determine the pH by looking at the reaction of the ammonium ion with the water in solution. Remember that because we're in solution, we can always write a reaction with water. To determine the concentration of ammonium prior to that reaction, though, we will need to determine the new volume of our solution. We know that we started with 30 milliliters. We added 0.006 moles of hydroiodic acid. However, we do not have in the question the volume that relates to that number of moles. So we'll need to solve for the volume of hydroiodic acid that has been added. To accomplish this task, I'll take the number of moles of hydroiodic acid in my initial column and divide by the concentration that's been provided to me in the question. We can see the concentration is 0.4 mole per liter. By dividing the number of moles by the concentration, moles will cancel, leaving me with a value in liters. So now that I know how many liters of hydroiodic acid I've added, I can determine the new volume of my solution. So I initially started with 30 milliliters or 0.03 liters of ammonia, and to that I've added 0.015 liters of hydroiodic acid. Therefore, my new volume will be 0.045 liters. You can see that I'm maintaining extra zeros to follow the laws of significant digits. In the question, I'm provided with 3 significant digits in my volume and in my concentration, so I'll need to carry those 3 significant digits throughout my calculations. With the new volume, and knowing the moles of ammonium ion produced, I can solve for the ammonium ion concentration in the solution. And maintaining my 3 significant figures, I get a concentration of 0.133 mole per liter. Now that I know the concentration of the conjugate acid produced from my initial reaction, I can determine the pH as though I was asked a question in which I was provided the concentration of an acid and asked to find its pH. To do that, we would start out by forming an ice table and looking at the reaction of ammonium with water. So let's write out that reaction first. Because the ammonium ion is a weak acid, we know that it will donate a proton, and water, being an amphiprotic substance, will accept that and act as the base in this example. That's why we form hydronium ion and ammonia. We have the initial concentration of the ammonium ion we calculated. Water will be in excess, so let's fill in our ice table and represent our change in concentration using X. Okay, now let's quickly look back to our first sheet where we solved for the concentration of the ammonium ion. We had a concentration of 0.133 mole per liter. So let's add that as our initial concentration to our ice table. In any of these examples, water is in excess, so we do not need to consider it in our ice table. So let's just cross that out. Now, we do not know the concentration of the products formed, so we'll have to represent change using X. So from our reactants, we'll lose minus X, and because the molar ratios are 1 to 1 to 1, our change in the concentration of our products will be plus X. So we now have an ice table with equilibrium concentrations being represented using X, and for the ammonium ion, we use the initial concentration minus X. We'll need the Ka value of our acid to solve this question. However, in the question, we were only given the Kb of ammonia. Because ammonium ion is the conjugate acid, we can solve for the Ka value by using our Kw relationship. We know Kw is 1.0 times 10 to the negative 14, and in the question, we've been provided with the Kb value, which is 1.76 times 10 to the negative 5. So let's fill that in. Okay, when we plug this into your calculator, you should get a value of 5.68 times 10 to the negative 10. And now that we have a Ka value, we can use that value along with the equilibrium concentrations from our ice table to solve for the concentration of the hydronium ion. That will let us solve for the pH using the pH equation. So we'll first write out the Ka expression. Okay, now using our values from our equilibrium portion of our ice table, along with the Ka that we calculated, we should be able to create a situation where the only unknown is X. Okay, so you can see that I'm going to have to do a little bit of math to rearrange and have a quadratic equation that I can use to solve for the value of x. By moving my denominator to the other side of my equation and expanding, I should be able to come up with an equation equal to x squared. Now I'll simply rearrange what I have to have a quadratic equation which I can plug into the quadratic formula and solve for the value of x. Okay, now that I have my quadratic equation, I'll use my quadratic formula and solve for the value of x. In case you forgot the quadratic formula, x equals negative b plus or minus square root of b squared minus 4 times the value of a times the value of c. And all of that is divided by 2 times the value of a. In the quadratic equation, a is the number coming before x squared, which in this case is 1. B is our b value, 5.68 times 10 to the negative 10. And c is negative 7.55 times 10 to the negative 11. So let's substitute those values into our quadratic equation. So don't do what I just did. Make sure to leave yourself enough room on your page to fit the whole thing. If I go ahead and solve, I'll get 2 values of x. Remember, we have the plus or minus term, so we will end up with 2 different values. The values you should get are x equal to 8.69 times 10 to the negative 6, or negative 8.70 times 10 to the negative 6. We know that we're solving for a concentration as represented here in our ice table. X is the concentration of hydronium ion. Because of that, we cannot have a negative value. We cannot have a negative concentration. So we don't have to consider that value of x. Because x represents the value of our hydronium ion concentration, we'll set the hydronium ion concentration equal to the value that we've found. Knowing the concentration of hydronium ion, I'll use my pH equation and solve for the pH. And when I punch the negative logarithm into my calculator, I get a value of 5.06, which is the answer to our question. Let's go back and take a look at all the steps we've done. In the question, we're asked to solve a strong acid weak base titration at the equivalence point. We're given the volume and concentration of the weak base as well as the concentration of the strong acid. And we're told that this is occurring at the equivalence point. We have to remember that that means all acid and all base will be consumed. I wrote my reaction and used that to fill in my ICF table. Knowing the concentration and volume of ammonia, I was able to solve for the molar amount, which I plugged in as my initial mole value. Because we're at equivalence, and because ammonia and hydroiodic acid react in a 1-to-1 molar ratio, I also needed 0.006 moles of hydroiodic acid, which resulted in the reaction of all of my reactants and the formation of 0.006 moles of my ammonium ion. As I stated earlier, we're going to ignore iodide ion because of the fact that it is a negligible conjugate base of a strong acid. In order to determine the new volume of my solution, I had to use the molar amount along with the concentration of my hydroiodic acid to solve for the volume of hydroiodic acid added, which was 0.015 liters. I then added my 30 milliliters or 0.03 liters of ammonia to my 0.015 liters of hydroiodic acid for a new volume of 0.045 liters. With that value, along with the molar amount of ammonium ion, I was able to solve for my ammonium ion concentration. Knowing that we're in solution, the ammonium ion will react with water, donating one of its hydrogens, which water, an amphiprotic substance, will accept. We formed ammonia, and hydronium ion. I represented this reaction in an ice table and plugged in my initial value of ammonium ion. I represented my change using X and double-checked for my molar ratios, which are 1 to 1 to 1, so plus X and plus X, which means at equilibrium I can represent my concentrations using the initial minus the change for my reactants and plus the change for my products. Because I'm working with a weak acid, I needed a Ka value, but was only provided the Kb. So I solved for Ka using our Kw relationship. I then wrote my Ka expression, plugged in the values that I knew, rearranged, and solved for a quadratic equation. Using my quadratic equation, along with my quadratic formula, I was able to solve for the values of X. I ended up getting two values of X, one positive and one negative. However, since a concentration cannot be negative, I only have to consider the positive value. As shown in my ice table, X is the concentration of my hydronium ion, so I set my concentration equal to the value for which I've solved. Knowing the value of my hydronium ion concentration, I was able to solve for my pH by taking the negative log, and I got a value of 5.06, which is the answer to the question. We were asked to determine the pH of the solution. So I thank you for watching. If you have any questions, please post them in the comments below.